Hello everyone, you're welcome to the other section on differential equations again. In the previous video on the linear equations, we were left with some question to solve, and I hope you've been able to do it. Well done. And I have a teaser here as a continuation. We have to find a solution to the first order equation given as what you see on the slide. And so you realize that there are certain questions you must ask yourself. That is this differential equation, because it's a first order, is it separable? You realize that it will not be separable, it would also not be homogeneous, and hence it means that you can't separate it. And then the next thing that will come to mind is linearity. You know there's a standard representation for linear, but look at what you have on the differential equation. It's as if my p of x is 1. I have k of x given x, but there's another term, y of x. This guy here does not make it linear, because I have k of x here, I have p of x here, I have my y here, I have my y prime here. There's an extra term introduced, and that leads us to the non-linearity approach. It means it is not linear. But let's see what we can do to this guy. So it wasn't separable, it wasn't homogeneous. What next? That leads us to non-linearity. The interesting thing about non-linearity is that we can make it linear. We can transform it to be linear because we know how to solve linear equations. Just as when it was not separable, we were able to make it separable using some transformation. And that is the whole principle we are going to use here. Okay, so if we want to go back to our equation, someone will say he or she is still not convinced about the non-linearity thing, but you would want to multiply through or divide through by y squared. You realize that you have this term, and we establish the factors for linearity. We don't expect a multiplication of the unknown function and its derivative, and that is what we see here, and that confirms that it is nonlinear. Okay, all right, so let's go back to the general approach for nonlinearity representation. In this case, we are considering the Bernoulli. If you have it in this form, this is the extra term added to make it nonlinear. The transformation we need is given as t1. In a separable, the transformation was just y equal to ux, and we had to differentiate y prime to get some terms, and we did a substitution. So in the same way, if I'm given this transformation, I have to differentiate it. This is the same as the u dy being equated to derivative. If you remember your differentiation very well, I have 1 minus n y to the power plus 1, that will give negative n. Derivative of power rule. This means that my du is 1 minus n y negative n dy. This is the same as u prime being equated to 1 minus n y negative n y prime, and that is my equation t2. This is as if you've done implicit differentiation. Unlike the separable approach, we did the product rule differentiation. So you realize that indeed the prerequisite for this course is calculus. So here is not a product rule, we end up getting an implicit differentiation, that is t2. So what do? The same approach with separable. You substitute your t1 and t2 into the differential equation. When you do that, it will automatically become linear. It will be transformed to linear, and then you go to the linear step. You find the integrating factor, you multiply, you find a product form, you integrate, you find your unknown, and that is it. But there's a cheat, a cheat sheet here. If you don't want to go through the transformation approach, there's a way to get a linear form. It says that if you have y prime plus some p of xy is equal to some k of x with a term yn here. You know this is nonlinear, right? If you want to linearize it, it says because we were using u equal to y minus n, you want to just use this guy here, and that's what I have here. So you take u prime 1 minus n multiplying whatever you have left, 1 minus n multiplying your k of x term, and this will give you the linear form. So all we need is to find the 1 minus n term, and then you fix it into your standard linear form. It will be linearized. So you realize that this is like finding u prime plus something p of x u equal to just something k of x, and becomes linear. Okay, so you want to use equation let me say equation 3 here. That is giving us equation 4 in my slide. This is the cheat form to get your linearity. So I'll still say equation 4. So I'll take you through examples, and we'll use both the standard form and then the equation form to see if the linearize is working. Okay, so let's take example 1. It says consider the Bernoulli equation. In this example, we are privileged to see the word Bernoulli, and what comes to mind is nonlinearity, nonlinear first order differential equation. Okay, if you're still not convinced and you know this is your linear form, you realize that in this case there's been an additional term here, and that will make it nonlinear. Okay, so the idea is to make it linear using the transformation u equal to 1 minus n, and then y prime we know is going to be y 1 minus n y negative n y prime. This is what we would have used. But assuming you want to use the cheat form or the smart way, it says don't worry about this whole transformation thing. What is needed is this guy here, or this one. So write your u prime, bring your 1 minus n, your p of x 1 minus x, and your q of x. It's as if you know the standard linear form is u prime plus p of x u equal to q of x. This should have been a linear form. So if you want to get it, it says multiply these terms by your 1 minus n term. That is all we are doing here. Okay, so let's see 1 minus n. In our question, it was this where your 1 minus n is coming from. Okay, so it means it is 1 minus 2, and that gives me negative 1. So my 1 minus n term is negative 1. So you have negative 1 multiplying here, negative 1 multiplying here. And what do we get at the end of the day? Let me clean this whole thing. It means I have u prime, negative negative gives a positive 2 over x u is equal to positive x squared. And now this is linear. This is the linear form of the question, and you can go through your linearity approach and solve it. Okay, if you don't want the smart way, you want to work the hard way, forgive me of the word hard way, but you want to go to the standard approach, you will still need your equation, nonlinear equation, and then what you do, you find a standard form by dividing through by this guy. If I divide through, this is what I'm going to get. Take your time and review that. Okay, then I need my transformation. I need T1 and T2. I've already established these transformations for you. T1, T2 have been established. So this will be equal to 1 minus n is 2. So I get negative 1. And over here, because 1 minus n is negative 1, I have negative y negative 2 y prime. N is equal to 2 from here. There's y to the power n. Okay, so it means my T1 equation, T1 u is actually equal to y negative 1, and my u prime is equal to negative this and then that. So this is my T1 now, transformation 1, transformation 2. this is what I'll substitute into my equation here. Let me see, equation star. That is a transform after dividing through by the y square. Okay, and let's see if I do the substitution, do I get it in a linear form? Let's continue. You realize that I have, let me rewrite the whole, negative 2y prime minus 2 on x y negative 1 is equal to negative x squared. We are doing the substitution together. Look at this guy. What do you see? It is equal to u prime. I'm rewriting the terms in u. So negative u prime. Why negative? Because this is a negative here, but this is positive. Okay. Minus 2 on x. Do I know representation of y prime? Sorry, y negative 1. Yes, it is u. So I have it as u is equal to my negative x squared. If I multiply through by negative 1, I have u prime plus 2 on xu is equal to x squared. Now this is a linear form. You should know that this is u prime plus p of xu is equal to k of x only. It is linear. This linear form, and then when we had using the cheat, what do I use to say cheat? Yeah, it's just a smart way. You realize that they are the same. There's nothing different from the linear form from the smart or the cheat form, and then going through the standard approach, it is still the same. And then you go through your linearity approach to solve this problem. Okay, but one thing you must notice that your solution now is in terms of u of x, but the original problem was y of x. So how do you find this? You realize u of x, you had from t1 you had y minus 1. The same as having 1 over y. It means y is equal to 1 over u, and then that will be your answer. Whatever you found from the linear form in terms of u, the solution, you just have to divide by 1 on that to get your y. As simple as that. So I'll not go to a linear form solution approach. No, we've already gone through that. Let me take example 2. What I'm interested in is for you to be able to transform it to linear. So that is my answer for example 1. See if you can get this answer. Okay. Now example 2, I have the equation given first order. By default, you should know that this will not be separable, it will not be homogeneous, it will not be linear. Why? Because I have an extra term here. Your linear form is y prime plus p of xy equal to k of x. I have the y prime here. I have p of x as x to the power 5, but I have k of x here with an extra term y to the power 7. So this is nonlinear. And because of the form, it is a Bernoulli. So what do we do? I would have used this transformation u equal to 1 minus n, where n in this case is 7. From this, if I'm comparing it to the nonlinear standard form, you realize that my n is equal to 7. If I want to use a smart way, I just have to multiply 1 minus n by p of xu, 1 minus x, n by the k of x. 1 minus 7 gives me negative 6. So it means I have u prime minus 6, then whatever I have, minus 6 q of x. Now someone might be confused of where the p of x and q of x are coming from. So again, if I refer you back here, this is your p of x, it is x to the power 5. This is your q of x, it is also x to the power 5. So that is where I'm taking those values from. So this is a linear form now. And then if you want to solve it, you know what to do. But let's look at the standard approach to still get the linear form. If I have my nonlinear equation, I'll divide through by the yn. yn is this guy here, so it means I'll divide through by y to the power 7 and I'll have this representation. I need my transformations t1 and t2. How did I get that? U is equal to y1 minus n. Because n is 7, it becomes -6, and then u prime is, if I differentiate this guy, I should get -6 y to the power -7. Differentiation, you subtract 1, and then my y prime, because we'll end up getting an implicit differentiation as I've gone through the first sheet. Okay, so I have to substitute t1 and t2 into the differential equation here. So let's do that. You realize that I have 7 right to the power -7 y prime. I have it here, but there's -6 attached to it. It means that y to the power -7 y prime is equal to -1/6 u prime, and that is what I have here. So this guy now becomes -1/6 u prime plus x to the power 5. Y to the power 6 is simply u. It is from t1, so that is what I have from me. This y to the power -6 here is what I have here, which is the u, and I maintain my x to the power 5. Now if I want to simplify this, I have to multiply through by 6 or -6 to do away with the coefficient there, and this is what I'll end up getting. Now this is the linear form. Multiply through by -6 and realize that that is what you have. Now compare the substitution and standard approach transformation to the smart way of getting the answer. They are the same, so it's up to you to choose which one you are comfortable with, either the substitution transformation approach or the smart way of doing this. If this becomes linear, what do? You find the integrating factor, you multiply by it, you find the product form, you integrate, you find the unknown. Again, the unknown is in terms of u. You must do a back substitution to get it in terms of in terms of y. Let's see how we do the back substitution. My u was equal to y to the power -6. So if I want y, this is the same as 1/y to the power 6. So it means that y becomes u on x to the power -1/6. I hope I'm correct with this substitution. Yeah. And this is how you get your solution. So again, I told you the important thing is to get a linearized form, and then you can go to the linear approach to solve it. My last example, as usual, let me see if I have the answer here. So this is my answer for, after linearizing it, confirm the answer for me. Okay, example 3, as usual, in the word problem. If you see a word problem, what do? You must take time and do your extractions. So the preamble, if you read carefully, it is talking about concentration of oxygen. This can be found in the biomedical field. Concentration of oxygen in our bloodstream and all that. Read it well and then you get it. So you ask yourself, has this been modeled by anything? Yes, I can see a model. This model is a differential equation. Are the terms defined? Yes, the terms are C, there's K, and then M. They are well defined in the preamble, so you must know them. Then you ask yourself, what is the problem I'm trying to solve? It is given as the blue sign. It says determine the oxygen concentration in the bloodstream at any time t. It means you are just looking for C of t to be something, and because there are no conditions, this is a general solution. Why? Because there are no conditions given. There's something like initial concentration of the oxygen is this, no. So it means you have the general solution at any given time t. So how do you solve this? I write my model down. 1, it is a first order differential equation. What is the class of it? Is it separable? Is it homogeneous? Can I reduce it to separable? Is it linear? Is it nonlinear? We've gone through. My handwriting is becoming bad. Let me do it well. Is it separable? It is homogeneous. It is linear, or it is nonlinear. You have to be able to figure out this very well. Automatically, this will not be separable. It will not be homogeneous, that is reducing to separable. It will not be linear, because there's a term here. You don't see y's, now you see c's. So you must be smart with these things. It's not always going to be y and x. Okay, this is non-linear, so I need a transformation of this approach. I always want to go with a smart way, so what I need is just this guy here, 1 minus x. So I write my u prime, because now the solution will now be in terms of u's. I need the 1 minus n term here, multiplied by my p. I need my 1 minus n term here, multiplied by my q. Because I want to write it as u prime plus some p of x u equal to some q of t. So it is in terms of t. To make it linear, so I just have to multiply these things by 1 minus n. And here n is 2, so 1 minus n becomes negative 1 here. So this leads to that, negative 1 here. Again, someone will be asking, where is my p of t? My p of t is this k here, and then my q of t is this m here. Forgive me of the circling of things, but it's to help you out. If I rewrite this, I have minus ku equal to minus m, and this is in the standard form. So it means that your p of t is the k minus k, your q of x or whatever is this guy. This is the linear form. So if you want to use the linear approach, you go through all this category, all this list, and then you'll be fine. Again, don't forget to transform your solution in terms of y of t. No, there's no more y, in terms of c of t. How would I do that? You realize that from here, your transformation will be u equal to c 1 minus n. C was 2, n was 2, so I get c minus 1. U equal to c minus 1. The same as having 1 minus c, and hence c becomes 1 over u. It means when I find a u, I just have to take the inverse of it. But there's another interesting thing happening here. If you look at your transformation very carefully, it's going to be separable. How? You should be able to figure it out. If I rewrite this as taking everything to right hand side, this is what I'm going to get. Do you see that? Yes. Now you know the y u prime is same as u, the t is equal to this guy here. By cross multiplication, I have, this is in the differential form. I have the u equal to whatever I have here, the t. And what do? I can divide both sides by negative m plus ku. Everything is here is in terms of u, everything here is in terms of t. Now don't be confused with the, because there's m and k. M and k are not of interest, they are constant value provided. The interesting values here are u and then t, and I've been able to separate it. So sometimes you would want to be smart by looking at the answers. If it's separable, then you go to a separable approach. You must get the same solution at the end of the day. So kindly try your hands on the linear form, solving by the linear method, and then looking at the separable method and see if you're going to get the same answer, and your life will never be the same. So far we've gone through 4 solution techniques of the first order differential equation. In my last lecture video on the first order, I'll take that of the exact. That is, if it is not separable, if it is not homogeneous, it is not linear, it is non-linear, what do you do? This is the last category of first order differential equations, and that is what I'll take next. See you.